We are continuing with class 4, and we skipped a little bit to the quick return mechanism because it makes sense to compare this to the previous example that we did, which was just a simple dyad. This is really example 3.9 that we're going to be working through, although we had previously did example 3.1. So example 3.1 and example 3.9 are very like each other. So a little bit of what a quick return mechanism is. Just like the name implies, it moves in one direction at a certain speed and then it comes back at a faster speed. So it's a quick return, right? And examples might be this Scotch yoke, where what we're doing is we're turning rotational motion into linear motion, and so it'll go quickly in in one direction and slower in the other, or vice versa. I can't remember which. There's a kinematic diagram of it. Another is this Whitworth, and this might be used for like a cutting tool. There's also other ones I've seen Whitworth for a film advance mechanism. These are all quick return mechanisms. And the big idea behind them is that we're going to use something called a time ratio. That's really going to be the ratio of this angle beta to that angle alpha. And so the relationships are going to be, I'll write them down. I guess my pencil is here. Okay. I was about to say it was MIA. Okay. So the time ratio is going to be, we'll write that down as TR, and it equals a ratio of this angle alpha to this angle beta. And if you look closely of what they are, this is when this thing aligns with okay, so this is the crank overlaid with the coupler right here and getting into this position versus the crank and the coupler in line with each other into that position. So you can see that the arc that gets made for that has a different length under one than the other, as opposed to the one that we had before here, right? Where here was the overlaid one right here, where this is the crank and then the coupler right there are overlaid each other, and here's the extended one, and they're in line with each other. So you can see there's the difference between. So we might want to look for that when trying to analyze something to see if it's a quick return mechanism or not. And once again, this is just a dyad design to achieve this right here. So you could maybe make when adding a dyad onto a mechanism, you want to maybe go back and take a look at this trait to try to have this property. And so to find this right here, another way, let me put it this way. There is a relationship between alpha and beta, obviously, that alpha plus beta is equal to 360 degrees, right? So you could replace it. I'm trying to, so talked out today. TR is going to be alpha divided by 360 minus alpha, right? Just subtracting, sticking that back in there. And the process to make this is to look for this angle right here that is formed in between, and just as a simple means right here, we can see that del could either be the absolute value of 180 minus alpha, or it could be del could also be the absolute value of 180 minus beta, either or of that, right? So what we do is we can, if we have a particular time ratio, we could go to this and solve for alpha, and then put this out, and then find beta from that, and then we take either the alpha or the beta, and we can find what this angle is between there. So let's take a look at a comparison between, I think it's this example right here. Yeah, this is example 1 that we did, where we just added a simple dyad. And if we take a look at the angular velocity of this part right here, so let's take velocity, we'll take angular velocity. Where's angular velocity? There you go, angular velocity. We'll take the component, the z component of it, and let's put it to that as the reference. So we're going to plot that, and you can see, unfortunately, the SolidWorks doesn't like do a very good job of showing you where the 0 is on this. It's actually probably easier to, so they're plotting like 1 right there for some reason. But you can see that it has pretty much the peaks. I think it does. It should, as it comes through. I don't know. It's interesting to me. I think we can go ahead. Can we click on this and go? Well, if you just go to this one, well, can you go export to spreadsheet? Let's go export to spreadsheet. Just see this graph. I don't know. I thought I was going to open it up. There you go. It did open it up. So this is at the time, right? Let me see. Let's plot it. Insert charts. Boom. And let's make this bigger. What is this guy? What's his value? He is, looks to be like 47.69, and what's his value? Come on. 46, so they're not identical. It could be just the precision of the math involved in this. You can change how precise they are by increasing the number of frames. You don't want to go too crazy, but if I go double it, go to 50 here, and recalculate it. It looks about the same, actually. It is still giving that maximum of 48 and that minimum of 46 onto here. So it's a little interesting to me that it's not exactly right. But if we go to, instead, go to, this is going to be the results of this analysis right here. This is going to be the quicker turn mechanism. Let's take a look. And I want to take a look at my graph right there. Let's just watch the thing in action. Right. So this is actually the magnitudes right here. Okay, so this is the linear velocity magnitudes. Let's take a look at the angular velocity onto the thing. Here, subcategory of angular velocity. Let's go magnitude of that here. And pick that as the reference and plot it. So yeah, well, that gives us pretty much the same trend right here, where we have a different angular velocity here than there, right, as it's coming through. So that's like the quicker turn nature. Let's do the same thing for over there. I'll go for the magnitude. No, that's the wrong one. Let's see. Is it that one? I don't know. Why is it not giving me the thing? Am I going to the wrong place? There you go. And motion study, and adding plots into there. Let me do the same one here as that one. It's the angular velocity. We'll go magnitude this time. Gonna put it onto there. Use this as the reference. Boom. They're pretty close to each other. They're still, the magnitudes are slightly different right here. But you can see the difference between the quick return mechanism. So let's see. I want to make sure that we're keeping track. That was 10 minutes into this. Let's do an example. And so this is example, yes, this is example 3.9 from the textbook. So where we have a quick return mechanism right here. They give us a procedure walking through there. So I couldn't recall it all that well. It will really help you to do these problems if you have a protractor, a good straight edge, a good ruler, like these right here. You can go to the bookstore and find this awful thing. It does have these inside here, so it has the green ruler, decent. I would prefer, I like my see-through one better with my tenths of inches. If you happen to be live in class, I will gift you one of these, my present to you. And if you're a remote student and I never see you, I owe you one. I just bought a bunch. Anyway, you could have the triangles and this not so great protractor because you can't quite see it, the thing. So it's I would go look for one. We'll help you out. You could also do the thing in CAD, and it helps it out. And it's a lot easier to do this. I have a video where I demonstrate doing it in SolidWorks. So maybe we will show that in class. No. All right. So this is also my practice, by the way. Going through the procedure here, we the thing we want to do is first we want to we want to find, we know the time ratio here. This is not a great video. So the time ratio is equal to 1.25. And we know that we had to find alpha divided by 360 minus alpha. Doing a little bit of math here, we can turn alpha as 1.25 times 360 divided by 2.25, and that's going to end up being 200 degrees. Yeah, okay, that makes sense. Yep. And therefore beta is equal to 360 minus 200, or 160 degrees. We have alpha and beta. We have del and be 180 minus the 160, or 20 degrees. Great. So we want to have an angle formed between two lines right here and right here, where that angle is going to be 20 degrees. The first line is a little arbitrary. Okay, so just be aware that we could pick this line. We could kind of pick them in there is a range about which it would work. There is a line. Not everything will work. But now, let's say if we were going to have like 30 degrees, that would be nice, convenient right here, that we could use a 30-degree triangle, and we could find where the other thing would intersect, and that's going to give us the center about which we would move onto the thing. But instead, we're going to use a protractor and try to find the spot on here where we would get 20 degrees. And so I am looking and looking here, so I'm going to mark, I'm using these in conjunction together, and I believe right there is going to get me 20 degrees. All right, that's pretty good. So I'm going to kind of guesstimate. Okay, I think that's going to be right. I'm going to double check on it. Yeah, that looks about right. Now in SolidWorks, it's actually fairly easy to do. All right, so I think I might actually want to reconsider and maybe move this thing over. It's pretty steep right there. And the next step that we were going to have from here is to label the intersection of the two construction lines as O2. So this is O2 right here. And then draw a construction line through B2. And then the line O2, O4 now defines the ground link. Okay, so this is now the ground link right here, according to the example that I just did. And we want to find the lengths of the crank and the coupler by measuring OB, O2, B1, and OB, O2, B2. So we're going to measure these two right here. So let's see. I don't remember doing this. So at least for my special ruler here, I have it's 3.65. Which one's that? That's going to be our O2 B1, and then our O2 B2 is going to be, well, that's really close. It's really close to, looks like 2.9. Okay, and according to this, we're going to take and say that the coupler minus the crank is equal to O2 B2, and the coupler plus the crank is equal to O2 B1. Okay? So using this, we can construct, let me pause. Okay, so what that means here is we could just use this formula right in here. So we could say that, for instance, let's say L3 is equal to this guy right here, 2.9 plus L2, right? And substitute back into here where we have 2.9 plus L2 plus L2, right, is going to be equal to 3.65. So L2 is equal to, I think I did that, all right, 3.65, 2.9 minus, and 2 divided, right? So that says it's 0.375. That's pretty small. I wonder if I did anything wrong. And therefore, L3 is going to be equal to 2.9 plus 0.375, and so 2.9, so plus it's 3.275, right? That's one choice we can make. It also says what we could do is take our, hopefully our compass is large enough to do this. We could take this at B2 right here, B1, and find that arc right here, and that this right here, this distance from here to here is going to be 2 times, and what they're calling is O2, A2, right? So to A2, which is the crank distance, right? So the crank length is it's going to be pretty small. So it's like 0.375 here. So to find the crank length, once we have the 0.375 from that. So let me try that. I mean, so if 0.375 is supposed to be the crank length, then this length right here, they're telling us it should be like 0.75. So we put this up there, and that looks like it's pretty close to 0.75, right? From there to there, yeah. So we want to do here, and trouble is this is a pretty small. That's pretty small for 0.375. This 0.375 is pretty small for this compass. See this 0.3. It's hard to see this, isn't it? Alright, so there's your 0.375 radius onto the thing. So right here would be the crank overlaid on top of the coupler. And then right here would be the crank and the coupler over extended. So something along those lines right there would be able to give us a design. I chose in a previous one, I chose a better / different configuration. So maybe I should have picked it a little bit better. So you see right there is where I've labeled it. So I'll try to do that in class and try to be closer to that one instead. All right, so I already have the SolidWorks version of this done. It didn't show the quick return mechanism here. This is close to being a Whitworth type of thing right here. So, and I think what a nice welding job they did right there. Trying to look at this and try to see how this is the same as that. I don't know. I'm going to look at this a little bit more closely and try to see, like maybe how the arc is different in this. But I don't know. You could maybe ask a student to write up an analysis to see how that compares. So let me go to another video.